In this tutorial, we'll be exploring convolution and pooling operations and how we incorporate these operations into our neural network models to create convolutional neural networks or CNNs. In our previous tutorial, we explored categorical data and we also designed and trained a simple dense layer based neural network to differentiate between the various classes of the MNIST dataset. How we do this is we flatten the image and feed all the raw pixels into our model. So there is a disadvantage to this approach. One, larger the size of the image, larger the model size, which is not ideal. And also neural networks that learn based on these raw pixels don't usually generalize well. So for example, if you see this sneaker on the right, there are some characteristics to it. One, it's grayscale. Second, it has a plain white background. And third, it is centralized within the frame of the image. So what if we see a new image such as this? It's also considered a sneaker, but it's facing in the opposite direction. It's an RGB image as opposed to grayscale. And also, most importantly, there are other objects in the background. So a simple DNN-based network, such as the one that we designed in tutorial 3, would perform poorly. Okay, so this is where convolutions come into the picture. So this is a concept which essentially extracts salient features and learn some sort of contextual information by considering neighboring pixels. So question 1, when a DNN is used to classify images, the raw pixels are fed into the dense layer of the neural network. Convolutions, on the other hand, extract meaningful features from the images and feed these into the dense layers of the neural network. So this is true, and we'll see this in more detail soon. Yeah, so let's look at a simple convolutional example to really understand the math behind it. The most important element of convolution is the kernel or the filter. And this is essentially a 3x3 or a 5x5 matrix of values that's applied on a source image to create your destination or transformed image. So for each pixel of our source image, we apply this filter and we slide this filter across the entire source image, left to right, top to bottom. And for each pixel, we perform this element-wise multiplication followed by addition. So let's look at some code that does this. We'll consider this source image, this grayscale image of a stairwell, and we'll first create our destination image based on the source image's shape. And most importantly, we'll define our filter. So we can define multiple filters. And the most important thing to understand is that the filter that we choose is based on the type of features that we would want to extract. So you could have edge filters, you could also have corner filters, for example. So here we are considering a horizontal filter. And this cell or this piece of code basically does the math that we've discussed, which is element-wise multiplication followed by addition. And this is our output or our convolved image with our horizontal filters. And we can notice that some of the horizontal features or the horizontal edges are more highlighted. Also, similarly, if we had considered a vertical filter, for example, some of the vertical edges would be more highlighted. So you can see the difference between this image and this image. Now that we've discussed convolution, let's discuss pooling. So pooling is another operation or a tool that's used in feature or detecting features. The main idea behind pooling is to reduce the overall amount of information in an image, but retaining whatever features or highlighted features that were extracted during convolution. So in this example, we're looking at a 2x2 max pooling. 2x2 indicates that that's the window size. So 2x2 indicates that we will be considering 4 pixels. And max pooling indicates that we'll be considering the maximum pixel value within that window. So here, in this 4x4 image, we apply a 2x2 max pooling to get a 2x2 image in the end. And each of these pixel values represent the maximum value within each window. So this piece of code is actually performing 4x4 convolution. So the number of pixels considered in a window would be 16. And this is the output that we see of the same convolved image, but after max pooling operation. We see that the features are more or less still intact, but we do see that the resolution has reduced by a bit. So our previous image was 512 cross 512, and this is 128 cross 128 after applying our 4x4 convolution. So question 2, what is the advantage of using pooling layers? The advantage is that we will, pooling reduces the size or the resolution of the image or the information required for processing, which helps in computational resources, but at the same time maintaining the highlighted extracted features or the salient features. Now that we've discussed the convolution and pooling operations, let's look at how it improves the performance of our classification models. So in our previous tutorial, we used only dense layers to classify the MNIST dataset. So let's look at that again. There's only one slight difference. We'll be using the fashion MNIST dataset instead of the MNIST dataset, which is very similar. It's 28 cross 28 grayscale images, and it has 10 classes. But instead of handwritten digits, it contains fashion items, such as sweaters and sneakers, for example. So similarly, we load the data set and we split it into training and test images and labels. Then we go ahead and normalize our images, and then we design our model. So in our model, we have a hidden layer of 20 neurons, and we have our final layer of 10 neurons reflecting the number of classes. Then we define our optimizer and our loss function and go ahead and train our model. So we see that we achieve a training accuracy of about 89% and validation accuracy of about 86%. So that was our initial model. So now we're going to look at how, by including convolution and pooling layers, this accuracy is going to increase. So what we do is we introduce convolution layers and we introduce pooling layers, but we introduce them before our dense layers in our neural network. And this is what forms a CNN. So CNN essentially is a group of convolution and pooling layers followed by our dense layers. And what the essence of this is that it reduces the amount of information going into the dense layers, and this information is more focused in a way. So question 3, what are the 2 additional types of layers in convolution neural networks? They are convolution layers as well as pooling layers. Okay, so similar to the previous model, we'll load our data set. We will split it into training and test images, and we'll normalize them. There is an additional step which is required by the convolution and pooling APIs that we'll be using, which is to include an additional dimension to indicate the number of channels. So since we're using grayscale images, this value would be 1. If we were using RGB images, it would be 3. So we do that for our training as well as test images. And then before question 4, let's look at this model design. So as you see, we have our dense layers as before, and we have a flattened before that. But before this block, we have 2 pairs of Conv 2D and max pooling 2D layers. So con 2D represents the convolution layer, and max pooling 2D represents the max pooling layer. So the con 2D, the first parameter indicates number of filters we want to apply to our source image, and the filters are of shape 3 cross 3. Max pooling 2 cross 2 indicates basically that we apply a window of 2 cross 2 or of 4 pixels, and within those 4 pixels, we always extract the maximum pixel value. So question 4, if a 2 cross 2 pooling layer is used, what percentage of the original image will be the new image? So if you do a 2 cross 2 pooling, we basically halve the vertical as well as the horizontal dimensions, resulting in an image that's 25% the size of the original image. We go ahead and look at the model summary. We see that we have a convolution layer followed by a max pooling layer, and then another convolution layer followed by a max pooling layer, followed by flatten, and then the dense layers. After that, we train our model, and we see that our accuracy now is around, training accuracy is around 95%, and our validation accuracy has also increased to about 90%. So so far we've seen that for the same data set, we're getting a higher accuracy or a higher classification, training as well as testing accuracy with convolution layers introduced, convolution and max pooling layers introduced. Now, finally, in our last section, what we'll be doing is we'll be taking 3 example images and applying these convolution pooling layers to them, and essentially trying to visualize what the features are, or trying to visualize the features that are detected. So specifically, we'll be looking at 3 images that are of class 9. So images that are at indices 0, 23, and 28. So if we have a look, we see that the image at index 0 is of class 9. And then the image at index 23 is also of class 9, and the image at index 28 is also of class 9. So these are the 3 example images that we're going to consider. And what we're going to do is that we're going to visualize the features extracted after convolution 1 and after max pooling 1 for all these 3 images. So if you remember our model, we have 2 pairs of con and max pooling layers. We'll be looking at the output after these 2. Okay, and that's what this block of code does. Convolution number 1 indicates that's our first pair of convolution and max pooling. And so this is the output. So the first image here indicates the output of our convolution layer on image 1, that is at index 0. And this is after the max pooling. And this is for the second image, and this is for the third image. So if you notice, this is around 26 cross 26, the dimensions, and this is 13 cross 13. So this is after the max pooling. So as you can see, these sort of outline the shoe or the sneaker, and these are the features or the highlighted features that are learned. So question 5, that's the last question of this tutorial. What do the 6 images above represent? So each row represents the convolution output of the convolution, as well as the output of the max pooling for each of the 3 example images that we've considered.